a new RPC endpoint is available on the master branch of Rusty Kaspa. It's VSPC version 2, and in short, it allows network observers such as exchange, payment processors, integration applications to get on DAG data more easily. Previously, when you wanted to get, for example, a transaction sender address of an accepted transaction, you would have to make 2 RPC calls in parallel, wire them with internal logic, and then make an extra RPC call. And now in one RPC call, you can get almost all data you need to create your system. We're going to introduce 3 concepts. The first one is selected parent, second one is VSPC, virtual selected parent chain, and the third one is what is a merge set. Let's see this simplified DAG here. And A is the past. It's either the genesis or the pruning point, whereas F and G here are the tips of the DAG. So every block in the DAG has a selected parent. So in the past, for example, D, it's trivial. It only has one parent, which is B. So B is the selected parent of D. And you can do that for every block in the DAG. For example, F, let's pretend the selected parent amongst D and E. Let's pretend it's E. So F has a selected parent that is E here. Both D and E has for selected parent B, and B has for selected parent A. We're not going to detail the rule to select the selected parent amongst parents. Now let's introduce a new virtual block that is in the future. So V is a non-existent block yet. It's in the future, it's virtual. From its perspective, it sees all of the tips of the DAG, G and F. And we're going to build this green line, which represents the virtual selected parent chain. And from V perspective, we're going to pick its selected parent, which is F in this example. And F already has a selected parent, which is E, etc., etc. Up until the genesis, you can build this virtual selected parent chain. When we say that a reorg occurs in Kaspa, it's when this virtual selected parent chain changes. For example, now for F, we are not selecting E, but we are selecting D. And so the VSPC now is VFDBA, whereas previously it was VFEBA. And so a reorg occurs. Let's introduce another concept, which is a merge set now for every chain block. So a chain block is a block that is part of the VSPC. For example, F is a chain block, but D isn't a chain block. It's not green. So every chain block has a merge set, and the definition is the following. A merge set of a chain block is all of its past, so DEBA minus the past of his selected parent. The selected parent of F is E, and the past of E is B and A. So the merge set of F is DEBA minus B and A. And so the merge set of F is D and E. In this context, we also call F the accepting block. It's the accepting block that merged D and E and accepted the transactions inside D and E. Without going too much into the details, a transaction can be included in parallel block. And so a transaction, let's say A, for example, can both exist in D and E, but only one will act as the source of truth in this context. This is defined by the global order in the GhostDAG protocol. What you need to know is all of these chain blocks have merge set that accepted transactions. That's all that matters here. So now we're going to see a bit more about the data. So this is a random block and it has some information that may be important for my use case. And it also has a transaction here. The transaction may contain some information I'm interested into, such as the payload, the transaction fee, the mass, for example, and also the inputs. I may be interested by who sent this transaction, what is the amount, and who is the target. In this example, the sender is the target and it sent a payload. In order to get all of this information, we had to make multiple RPC calls, and now with VSPC version 2, we can get all of that in one call. This endpoint takes a parameter. So for example, if I send block hash of A here, it will return every transactional data contains in this set here. I will have access to any chain block hash here, as well as transaction accepted by this chain block, and the transaction will be populated with almost any data, payload, gas fee, mass, etc. So now let's see how to use it. I'm in a JavaScript file using the WASM module, but you can use the Rusty Kaspa crate directly. If you have a Rust-based stack, it's even better. But here it works with JavaScript well too. You can initiate a connection using this block here. So this is connecting to my local node, but if you don't have one, you can just do that. It will work. This is using the PNN infrastructure that is community maintained. So the local node. Then we will fetch basic block DAG information that will allow us to access some of the data, and the one we need is is pruning point hash here. Once we get this pruning point hash, we will be able to call our endpoint, and we pass the pruning point hash here. So this is the starting point. We say we want at least 300 confirmation before receiving data from this endpoint. This is useful for exchanges that needs some wait time, let's say, confirmation before ingesting data. So just to summarize and make sure it's clear, the more you wait, the more confident you are that the data will not move. So once they are accepted, by waiting 300 confirmation, I'm fairly confident it will never revert or be unaccepted. Then we will be just to have a quick overview, we will be iterating through the accepting transaction for each chain block that we saw previously. If you're interested in the chain block header, you have a few interesting data available here. And then for the transactions, we filter by like we will only be logging the one that have more than 0 input, because if they have no inputs, it means it's a coin-based transactions, and it's not interesting for us. So we'll be logging a few things: the transaction ID, the sender address, the receiver address, the amount, the mass, and the time of the transaction. And if we execute the script here, so if we look at this one, for example, we can see it's some address that sent an amount to itself, and it was done yesterday. I guess it's near the pruning point. Then again, looks like it's the same address to itself again, the same address to itself again, another address but also to itself. And if we go here, for example, yeah, here it is a different address. Let's take this ID and go see on the Explorer. It's a bit more complicated. It's a compound transaction. Here I only logged the first input sender address, but in this case you would also want to log the other ones. So that's it. If you have any question, please reach out to me and I will try to answer the best I can.